let's go ahead and continue our discussion about organic compounds now. We talked about ionic bonds, we talked about covalent bonds, we talked about water. Let's talk about more of the covalent bond stuff. This is the result of covalent bond goodness. Organic compounds are always contain carbon in it. And because, well, carbon can bind onto 4 different things if it really wants to. Carbon compounds, they don't really like water. You have to have some extra things to get water into it. But carbon compounds also really are a good source of energy. These are groups that we can talk about that help make it more likely to go into water, but you don't need to know hydroxyl. You don't need to know sulfhydryl. You don't need to know carbonyl, carboxyl, all that stuff. Just know that oxygen, nitrogen, hydrogen, sulfur, phosphate, and well, I already mentioned nitrogen. Yeah, all can bind onto carbon and give it a specific feel, make it different. With that, because carbon is so unique, we can make it into different types of molecules. We're going to start off with carbohydrates. My absolute favorite. I really hope I never get diabetes. But I'm guessing with my office filled with a bunch of chocolates and sweets and treats, if I kept on eating it, I'd probably end up making my body hate me and glucose, and life would be awful. So first, let's go over some terminology really quick. We got saccharides. Saccharides just mean carbohydrates, sugars. And then we can go with the mono, di, and poly. Mono means one. So monosaccharides. Disaccharides means that you have, well, 2 of the monosaccharides, but put together. And then polysaccharides is just a bunch of monosaccharides, but stuck together via covalent bonds. Examples of monosaccharides would be glucose, which is that really, really sweet stuff. Really good. It makes anything that, like sugar, pretty much, is any simple sugar, cane sugar or those cubes of sugar or sugar that you add into any mix is usually glucose or maybe even fructose. It really adds some sweetness to your life. Disaccharides, these are the stuff that do need to get processed before being absorbed. Like lactose. Lactose is a sugar. It's just some glucose and galactose stuck together. And then there's the polysaccharides. There's 3 of them that you're going to care about. The glycogen. Glycogen is the stuff that animals store sugar as. So if you eat liver, then that's where a lot of the animals' sugars are being stored. You get a little bit in the muscles too. It makes sense that you'd have sugar there. You could have starches. That's like your potatoes, some of your other vegetables and stuff. You lose the sweetness here. And this is your pastas and things like that. You lose the sweetness. But if you have like a bland noodle or something, go ahead and stick it in your mouth, chew it up a little bit, get it really well emulsified, and sooner or later you're going to be tasting something sweet because you have an enzyme that breaks down those polysaccharides called amylase. So you don't need to know amylase right now, AMP4 again. But yeah, it'll eventually break it down into its monosaccharides and you'll start tasting something sweet if you're willing to feel mush in your mouth for a long time. And then there's cellulose. Cellulose, when people say, hey, eat your fiber, it's this. 90% of the time it's this. They might give you some like liquid fiber that's mimicking sugar. Like magnesium citrate kind of has a thing to it, or there's some other metamucils and things like that. But anyway, cellulose is the natural one. Your body can't break down cellulose, so pretty much once you eat it, it goes out the other end. So like corn, celery, anything that you can see after the food travails your digestive system, you go, oh yeah, that's still what that was what I just ate a day or 2 or 3 ago. Yeah, that's made of cellulose. Unless you're really weird and you're eating plastics. Anyways, I digress. So here's the examples of what monosaccharides look like. Again, it's that little ring thing. Disaccharides, it's the little ring things, but they're holding hands. And then there's the polysaccharides. This one's actually could either be glycogen or starch. Cellulose is really looks like a bunch of mesh or a sheet of glucose. It's really pretty. Okay, that's carbohydrates. Let's talk lipids now. Lipids, you probably could remember that if you add some type of oil, like vegetable oil, animal fats, or something like that, to water, they don't really mix well. They one sits on top of the other, like they just it's like a party where the nerds are on one side and the popular kids are on the other side. Don't try and guess which side I was on, because I didn't attend. It makes life easier that way. But I just laughed at my own corny joke. I'm sorry. So, lipids, and it also explains why when you try to throw some water or you accidentally throw some frozen chicken or frozen turkey into your boiling hot oil, that you get an explosion, because really water and oil really hate each other, but when you add heat, you add the energy to be able to fuel that explosion. So you got a lot of different things that add or are part of the lipids. You got fatty acids, triglycerides, phospholipids, steroids, eicosanoids, and other lipids like your different types of lipids. Fatty acids and triglycerides sort of come together to make phospholipids, so I'm going to go ahead and just switch over to that really quick. Here's an example of a phospholipid here. Phospholipid fatty acid here. You can see that, remember how I said carbons don't really like hanging out with water so much unless they have like oxygen, nitrogen hanging on that. Yeah, you don't really see any. These guys are going to be floating on top of water. This is a saturated one. Saturated means that it just has a whole bunch of hydrogens hanging out here. While unsaturated fats are like, you can see that little kink right there. These two carbons gave up hydrogens in favor of double bonding together. Yeah, that's what saturated and unsaturated means. Now, you can stick a triglyceride, one of these like ester linkages type of things going on to these fatty acid tails, so they've combined this fatty acid, these three fatty acids together, and it's become a triglyceride. I wonder why it's called tri. Now, tri, 1, 2, 3, means 3. Now, moving on, a phospholipid is really just those triglycerides coming together to form a layer. Those fatty acid tails going, no, we don't want anything to do with water, so let's intermix with one each other, but there's water here and water over here, so this is a phospholipid. It's sort of there to help put its fatty acid tails there. So really, your membranes, your cell membranes are made of phospholipids. Your cell membranes are made of phospholipids. Your cell membranes are made of phospholipids. I said it 3 times. There are other things that don't really like water. So like cholesterol is something that doesn't like water. If you take a look at it, these little rings, it's not noting that these little points on these hexagons or this pentagon thingy, but that's just a carbon. Those are just carbons. So you got a bunch of carbons hanging out here, and if you remember right, carbons without any oxygen, nitrogen, or sulfur, or phosphate for that matter, doesn't bind onto it. Well, you're not going to get any interaction with water, so it's a fat-loving thing. So cholesterol, that's what that looks like. Cholesterol is good for a few reasons. You don't want to like completely remove cholesterol from your diet, because for males it makes testosterone, for females it makes estradiol, and then for both it makes cortisol, which is your stress hormone, which is good if it's not a chronic stress issue. I mean, cortisol is there to help you make certain that you get the energy that you need in a stressful situation, but if you're continually doing it, it gets tired of its job, and then you get Cushing's disease, which basically makes you look like a baby and all the fat builds up on your belly and you get a hump on your back. Now let's go on to the next type of macromolecules, biomolecules that we're going to talk about. This is proteins. Proteins are really neat. They're awesome. They are like your functioning portion of your body. Everything that has some type of role or some type of functionality most likely is run by some type of protein. Enzymes are proteins. The little ports that let salt in or out of a cell, those are proteins. Those signaling molecules, a good portion of them are proteins, minus steroids and icosanoids. I digress. Moving things across and through the blood, like things that don't like water, steroids, are moved by proteins. They also act like protection because, like, immunoglobulins are proteins. Your muscles are made of protein. Like most of the functioning, all of the functioning unit of a protein of a muscle is protein. So really, there's a lot it can do. There you go. This is what it does. Now, proteins are really, really long strands of these guys, amino acids. There's 21, or I think they're still debating over 23, but right now it's a guaranteed 21. And you don't need to know every single one of them. Just know that their main characteristic is that they have this group on one side, on the right side, this group on this side, a nitrogen with 2 hydrogens, and then in the middle they could have some type of special thing. It's called a side chain. It could be one of these, it could be one of those, it could be this, it could be that. There's tons of them. Okay, I shouldn't say tons of them. There's about 21 of them. Now, in order to make a protein, these guys come together. You ditch a hydrogen and oxygen, a hydroxyl group it's called. And then when they ditch that, it forms a bond. It's called a peptide bond. And then more can be added on in sequence. If you want that, and these can be added into sequence, that's called a primary structure, just telling you the order of your amino acids. These amino acids can interact with one another. Some of them could have an oxygen nitrogen on them. Some of them could just have a chain of carbons, pretty much telling you what they turn into. It could be an alpha helix or a beta helix. These are secondary structures. Moving on, this protein can fold further or change its shape further by determining how much this alpha helix, how many of these beta pleated sheets and these alpha helices can come together and interact with one another. The quaternary center is like taking one of these proteins and seeing if there's another protein that wants to come together and do something. So multiple proteins coming together is quaternary. So let's review really quick. Primary is the amino acid sequence. Secondary is how those amino acids are interacting. Tertiary is how these are interacting, the alpha helix and beta helix. And then quaternary is trying to see how multiple proteins are interacting. Now, again, these proteins can become enzymes. They can be for you, in A&P, we're going to assume that they're extremely specific. You can't have anything else go into it. So, like, if you remember, sodium and potassium both have a positive charge, but their size differs just the tiniest of bit because of the number of protons it has. You wouldn't think that wouldn't be a big issue, like the smaller one could still sneak through, but no, it doesn't. It only lets the sodium in through a sodium port. It only lets potassium in through a potassium port. It only lets a hydrogen in through a hydrogen port. It's really neat. It's really interesting. Enzymes is the same way. If you want to metabolize glucose into something, you got to use this specific enzyme. There's no other enzyme you can use to get it all started. When you get into pharmacology, that's going to be a different story. Like, there's contraindications that it's called, where, for instance, you don't want to give one drug at the same time as another because they use the same enzyme and bad things could happen. I shouldn't say drug, I should say medication. Although there are cases where you don't want to mix drugs with medications either. Now, enzymes have a really, really specific site called an active site, in which this is the reason why you can really only get one substance to go in. It goes in, and only that specific perfect shape will allow that specific perfect molecule to get in and then be made in from a reactant to a product. if that enzyme changes shape at all, its ability to do things changes as well. That's why maintaining a body temperature at 98.6 is really important, because if you get up to 101, 102, you're starting to change the shape of an enzyme, you're starting to change the shape of your proteins, and that's not good. You don't really do a good job at processing things at a different temperature. Finally, a last group, the nucleic acids. Nucleic acids make up DNA and RNA, both of which are really important to build us. It's like the building blueprints. DNA building blueprints for RNA, and RNA is the blueprints for protein. We're going to talk about that next week, week 2. Each one, both DNA and RNA, contain these three right here: cytosine, adenine, and guanine. Adenine and guanine like each other. Adenine likes either thymine or uracil, while guanine really likes cytosine. Now, if you're talking DNA, DNA really likes thymine. In DNA, you're going to only see thymine. In RNA, you're only going to see uracil. Thymine will not exist in RNA. Uracil will not exist in DNA. These guys are added onto a sugar. If you're in DNA, the sugar is called deoxyribose. Kind of the reason why you see the D there. Deoxyribose is the D. Na is the nucleic acid. Yay, it makes sense now. Ribose kind of explains why it's RNA. Ribo, nucleic acids. Yay, it makes sense now. In DNA, again, adenine really likes thymine. You're never going to see uracil in DNA. There's something wrong if you see uracil in there. And you're going to see guanine, cytosine. It is a double helix structure, meaning that it has two strands. One strand is on one side, the other strand is on the other. They're interacting with one another, and it is always A and T and always G and C together. They will never be separate. They're their best friends. RNA, well, RNA is just a single strand. RNA, you can see right here, is just one strand. This list is really important to remember. We kind of already talked quite a bit about this to discern between the two. You will need to be able to discern between the two. I'm just going to go ahead and tell you that now. DNA, again, there's the nucleic acid bases: adenine, cytosine, guanine. Look at that. RNA has those three. But what's the difference? Thymines in DNA, uracils in RNA. What type of sugar does it use? Deoxyribose. What type of sugar does it use? Ribose. Ah, neato burrito. Number of strands, 2 in DNA, 1 in RNA. Notice again, this is kind of a repeat for the top one, except for A goes with T and G with C, but in RNA it's A with U and G and C with C. DNA, when you do mitosis, when you divide a cell, that's what mitosis is, it has to replicate itself. You gotta make certain it's perfect or you're no longer you. RNA is just a piece of information being sent out from the nucleus, because the DNA really doesn't like, is an introvert and doesn't like leaving his home, the nucleus, unless it's absolutely necessary, like during mitosis. So it's going to send out RNA as its messenger to say, hey, we need to make this protein, go get it done, chop chop. Or it could be other types of RNA, which we'll talk about later. And with that, that's about it. Except for this one last one. They sort of just threw in randomly because they thought it was a good idea, I suppose. Adenosine triphosphate. We're going to talk about that next week. But adenosine triphosphate, if I were to summarize it, is the money currency of your cell. It's the thing that gives energy. You break off one of these phosphates, a whole bunch of energy gets released. Phosphate, by the way, is 1, 2, 3, 4 oxygens attached to a phosphate group. Phosphorus group. Phosphorus, blah, 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 blah. Atom. So, once that's released, it releases a whole bunch of energy, and that's just what your body really likes, is that energy. So, storing that energy in this form is great, especially when you're a little low. Helps out with a lot of things, with like breaking down things or building things up, making new protein, things like that. with that, that is it. Thank you very much. I hope you have a pleasant day.